about to continue.
Once we've both said our goodbyes, let's just let it go. Let me let you go. Quiet when I'm coming home and I'm on my own. Like it like, say I like it like that, like it like that. I could lie, say I like it like that, like it like that.
Ladies and gentlemen, please sit down. The show is starting.
All right. Rule number one at conferences, check your watches. Mr. Hall, Tim Hall, please take your seat. Evan Kaplan, please take your seat. Paul Dix. Running out of people I know back there. Okay, let's get ready to get going with a deeper dive. I mean, just if I keep looking there, they'll feel embarrassed and walk back and take their seats. This whole like power kick I think I have. All right. So one of the bits of feedback we got, obviously every time we do one of these, we go and say, hey, what do you guys think? And we'll send a survey out to you as well, is we need to go deep and we need to understand exactly what's going inside the database. So I told Ryan, so sort of preparing this thing is like, Ryan, you need to go deep on the database and you need to make it understandable for mere humans. And so Ryan runs come on stage, Ryan runs our platform team, and he's going to sort of dig down into the database, what's happening in the database, and how do you scale a time series database. Welcome. Enjoy.
Good morning, everyone. These are bright lights. How is everybody? So thank you for coming today. It's great to talk. I guess there's a clicker to advance some slides. Here we go. All right. So my background, I've been building infrastructure software now for about 20 years. I've done that in lots of different ways, as a developer, as a tech lead, as sort of a principal architect, as a CTO, and now at Influx as the director of engineering, where I'm basically responsible for the teams that actually do all the hard work of building the data management components of the product. I get the easy part this time around. So what I'm going to talk about today are some of the things that I've learned in watching Influx users use the database, kind of what I think are some of the strengths and weaknesses of the system, and some of the things that I pay attention to as we go to implement the vision that Paul's outlined and try to make a better experience for all of our users. So let's get started with that. We're really going to talk about a number of different aspects. So this talk is a little bit more of a survey talk around different aspects of the database. I'm going to talk a little bit about lessons I've learned about the ecosystem in terms of working in a time series space, about some things around the storage system, clustering, query, and then as much as I hate to use the word disaggregation, I couldn't think of a better term here, but what I think about in terms of scaling query and storage and some of these different features separately from one another. So I think one of the things that I've learned most about coming to a time series company is exactly how ecosystem-related time series data is. The things I've built before were a little bit more isolated and a little more siloed, but I think certainly to succeed in the time series space, you have to think about how to build a system that fits into a community of products. I gave this talk previously and I tried to make a joke. It went over really flatly. We'll try it again. I think if you want to be good at time series, you have to be really good at being frenemies, right? I think there's a lot of co-opetition in this space. There's a lot of products that interact with each other that overlap slightly. But it's really critically important for end users to be able to assemble these things together and expect them to work together smoothly. And so the first major thing that I've learned about building a time series system is that you have to think about the extensibility and the integration of that system, and you have to think carefully about what are the core components of the system that have sustainable value to us as a company versus what are the parts of the system that are really more valuable when they're opened up for extension and contribution by others. And from an engineering kind of director perspective, one of the most interesting parts of that actually isn't technical. It's about how do you deliver software to such a broad variety of audiences. Right? So typically if you deliver a product, traditionally you deliver it in a certain way to a certain person. Right? So maybe you build a SaaS company, or maybe you build a shrink-wrap software company or services company. What I really find here in this space is that it's necessary for Influx and for our development teams to become good at shipping software to a broad number of types of consumers. And this involves very different engineering processes. It involves taking input from a large number of sources. And it means becoming good at both operating a system, right, a SaaS system. It means becoming good at managing and building a community. It means becoming good at offering enterprise support to our end users. This has actually been one of the most interesting challenges for me to think about at Influx, is how to build competencies along all of these different axes. And I actually think that if Influx kind of continues to grow and succeed, it'll be in large part because we learn how to manage all of these different constituencies, delivering to them the components for time series management that we build. And so my takeaway here is that the first thing that we've had to learn how to scale isn't really a technical thing at all, but rather we've had to learn how to scale the teams and the delivery and the release processes that we use to kind of give value to these different sources. And as we go forward with that, I think that there are places where we've done this quite well, places where we've made some nice improvements, and there are honestly other places where we really need to improve. One of the places that I would like the database and data management team specifically to improve on is on the open source community engagement side. As we've been going forward over the course of the summer and building out a lot of the components for 2.0, we've been working a lot on Flux. I think you've probably seen, if you're engaged community members, a little bit of a less attention to some of the InfluxDB repo issues, certainly a little bit less attention to some of the capacitor repo issues. I think it's super important that we kind of re-engage on some of the technical side with the community, and I'm very excited about some of the technologies that we're building in the 2.0 landscape that I think will make that easier. Paul talked, for example, about some of the intentional extensibility of Flux in terms of making it easy to contribute sources of connectors to destinations and syncs of connectors and transformations. That's one example of where we've started to formulate or reformulate some of our core technologies to enable us to better engage with the open source community, right? One of these core audiences that we want to get better at shipping software to. So kind of transitioning from some of the softer stuff, I want to talk a little bit, as Mark had referenced, about some of the internal aspects of the database and what I've learned in terms of trying to scale that as we've supported customers in larger production installations. To do that, I want to just take a step back and kind of talk a little bit about why a time series database. I talk a lot about building a database is hard. It's not something you should take on lightly. It's a large responsibility to take responsibility for someone's users and for those users' data. And so I think it's always good to kind of review why to build a time series database. So I think a time series system really has a number of unique characteristics that it needs to implement that distinguish it from other data management technologies, like SQL systems or sort of traditional document-oriented NoSQL systems. First is that a time series database has to have a very scalable ingest path. It has to be able to read thousands to millions of points per second, ingest and write those points, and persist them so that they can become queryable. And so a system that can scale the ingest path is very important. It has to be able to store that data efficiently, and then it has to be able to allow relatively sophisticated queries against that persisted data. This is actually in contrast to a lot of NoSQL systems that perhaps are very good at scaling the ingest of data. They can write documents to disk in a way that's efficient. They can append records to disk in a way that's efficient, but they tend to limit themselves on the query functionality that they offer, right? They'll have more simple document lookup kinds of functionality, or maybe simple document filtering functionality. In the time series space, though, it's actually critically important that we offer a sophisticated and fully featured query language that's capable of filtering data, windowing data, applying relatively complex transformations to data, performing arbitrary joins and math across the different tables of data that are returned. And so this combination of being able to ingest records quickly, but then also allow relatively sophisticated query language against them is something that's relatively unique in the time series space. So to do that, the database, has adopted what's kind of a log-structured merge tree-like storage format. What this means is that data arrives at the system, it's persisted first in memory, organized, and then written out in columnar blocks to disk. And those blocks are then later assembled and merged with one another through a process that's called compaction, over time creating longer and longer runs of time series data. Those runs of data are stored in what we call TSM blocks, and then they're actually written to disk as essentially an array of blocks within a single file. And here's really the first place I think we've seen in large installations issues around scaling the time series database. And these TSM formats require this kind of ongoing compaction process, meaning that you have to kind of take blocks and merge them together to create longer blocks. And compaction is a resource-intensive process, right? It's CPU-intensive and it's memory-intensive. Both of these things have created issues around scaling the database. I think anyone who's looked at the database and used it under a large amount of load or a large amount of pressure has seen that this compaction process can be quite challenging. And so I'm going to talk a little bit about some of the things that we've done to improve that over time. Another issue kind of algorithmically with log-structured merge trees is write amplification. So as you go to merge this data to disk, you actually end up writing the same points to disk multiple times. Right? So the first time you receive a point, we journal it to a write-ahead log for durability reasons, but then we write it to the first kind of generation of data. We come along and we compact that generation into a second generation of data, meaning we've now written the point to disk 3 times. We generate another generation of data as we kind of recompact and remerge those logs into longer and longer series of runs. And what you see is that every time you have to do that, you're actually increasing disk I/O. You're writing the same point to disk many times as you sort of continue to reorganize it on disk in order to kind of land it into its final representation. Now, to some extent, because as Influx compacts data, it's also columnarily compressing that data. It's using different like run length encoding and different compression algorithms in order to create a denser representation. So to some extent, we minimize write amplification because we don't pay the full overhead of writing the full data for a point for every time, right? Every time we write that data, we can apply some amount of more and more sophisticated compression, and so we can represent that data in fewer bytes within each generation of TSM. There's also a trade-off here in terms of write amplification and compaction memory and CPU utilization. Again, and this is a sort of an algorithmic thing that's common across all LSM-style databases. So as you're doing this compaction process, you can really approach it from 2 perspectives. You can say, I'm going to take all of the data in a certain generation, right, in a certain tier of this log structure, and I'm going to merge it all at once, right? That basically means that kind of, you can think of this as kind of at worst case requiring 2x the resource. You have to have enough resources to read all the data, and then you have to have enough resources to merge that data and write that merged data out to disk. Right? So it's kind of like saying I have 2 big piles and I want to merge those 2 piles together, and so I need to read one pile and read another pile, combine them, so now I have a pile that's twice as high, and write that pile that's twice as high out to disk again. So I kind of at some point in time was managing 2x the total resources, right? The 2 original piles and then the union of those 2 that I had to write back. So some LSM systems will try to combat that by allowing you to do incremental compaction. So instead of saying, I have 2 piles of data, let's say I like to take the top 10 cards off of each 2 pile and merge those together and write that. And then take the next 10 and merge that and write that. So basically, they create incremental units of compacted results that reside on disk. The problem with that is that you've increased the write amplification problem, right? So now to get to the fully compacted part, once I basically have split and merged subsets of that data, I now need to go merge those subsets and write them back. So the smaller I subset the data that needs to be compacted, the more often I end up writing the same point to disk over and over. So all of these things are trade-offs essentially between the ability to append data very rapidly to the database in a linear fashion versus the extra I/O you need to do to organize it after the fact to put it into the format that's sufficient for long-term storage and query. Another interesting problem that you see that's also related to compaction in the database is backfilling. So most use cases in a time series system are appending data that's relatively new in time, right? You're receiving new logs and new metrics. It's, however, extremely common to want to take data that was either very late arriving, it was on a server that was not available to the network, and it's now recording logs back into the system, or perhaps you're taking data from one system that was historical and loading it into another system for various comparison reasons. You need to then essentially backfill or bulk load that data into the database. When you do that, you're essentially disrupting all of the data that's been organized and compacted. So the TSM files organize data temporally, or they organize data in time, and if you go provide old data, that data needs to be landed and then recompacted into that data that was already organized the way you wanted it. And so you can see, again, that the cost of compaction has to be paid anytime that you produce a large number of new points that need to be threaded into the historical records on disk. Another issue with systems that are compaction-oriented are deletions. So as these files are compacted and written to disk, once they're finished, they're essentially immutable. And so deletions are not like in a B tree, they're not actually removing data or leaving a gap in the file. Rather, what happens is we write out something called a tombstone. We basically just write a record that says, hey, when you read this, just note that that data is deleted, so don't show it to a user, right? It's kind of like a soft delete or a tombstoning process. So as you perform a delete, you actually start accumulating these tombstones, right? Records of things that you're supposed to have forgotten, which is kind of ironic, maybe. And then you basically resolve those tombstones through this compaction process again. So it's actually surprisingly common, and this is also a little bit surprising to me as I kind of learned more and more about production use cases for Influx, to see range deletes with a predicate, meaning someone would like to delete all data between time A and time B that matches a certain filter. This happens primarily when someone has a system that inadvertently wrote data to the database that they just don't want to be there, right? An agent was sending bad data, a team somehow messed up a tag value, someone created something they just don't want in the database, and so for the block of time that that error was present in their system, they would now like to remove all the results of that from the database. These bulk deletes also then trigger this compaction overhead. And so the final aspect of this log structured merge tree is really quite maybe technical to the database, is that while the file format in its final compacted state is actually very, very efficient, we can store a large amount of time series data on a relatively small number of bytes on disk, at early generations, it can actually be dramatically inefficient. So if I go back a slide, you can see that we have all of these blocks of data, and then we maintain this thing within the file that we call the TSM index. And this TSM index is basically a list of all of the series that are present or represented or that have data blocks in this file and the offset to the block for that series. So in the case where you're at an early generation and you have not had the opportunity to combine a large number of points for a series into a block, meaning each block represents a relatively small period of time, this index space can actually dominate the TSM data, the actual time series data that's stored, meaning that essentially the table of contents for this file, where to find the different blocks, is larger than the content of the blocks themselves, right? And this is something else that we've seen. So all of these various issues are things that we've been working on. There are also things that have played very strongly into how we've thought about organizing data in the 2.0 system. There's not a lot that we can do about write amplification. It's a relatively intrinsic algorithmic aspect of log structured merge trees, and that is an extremely common data structure for databases like ours. It's used by systems like ROX and Cassandra and others. Right? So it's sort of just a trade-off that has to be made algorithmically. In terms of compaction memory and utilization, we've introduced configuration settings to try to allow people to control the number of concurrent compactions that are ongoing. Also in our 1.7 release, there's been a fair amount of rework of some of the base level readers and writers of this data, of TSM data, to allow vectorization and much more efficient instruction, basically execution. So at the lowest level in 1.7, in the best case, we can now read from TSM at almost 100x the speed that we could before, and we can write to TSM at about 10x the speed. The writing is a little bit more expensive because of some of the encoding that has to happen. So there's a lot of just kind of very low-level optimization that's gone into this, and we hope that as these things roll out into production that we see some decreased CPU utilization. Of course, you won't see the full effect of that because there's a lot of overhead in addition to just the purely reading and writing of data, but we have put a fair amount of effort in the 1.7 release into the low-level interfaces that do that, driven primarily by the impact that compaction has, and then also by some of the efficiencies that we would like to give to Flux. We've been writing more and more offline tooling for TSM data, so we now have tools that can do offline compaction of TSM data. We have more and more tools that will allow you to do things like inspect a TSI index, another file format that's on disk, to understand sort of like contents of measurements, some of these things. This has actually been surprisingly powerful. My inclination is to want to integrate all of these things into the database properly, but as I've been working more and more with support and with customers, with all of you, that we've certainly seen situations where having some of this offline tooling is actually quite powerful, much more easier to use, especially when something's going wrong in the database. And so I think we'll continue to try to invest in making these file formats open and understandable as much as we can so that we can produce tooling that can be used in operational settings where sometimes the database might not be doing quite as good of a job as you would like. So that's a little bit about TSM, kind of what we're thinking about. As we kind of go through the 2.0 cycle, we'll certainly be thinking about how to reduce the total overhead of compaction and how to reduce the impact of things like backfilling and ranged deletes. Another area that I would like to talk about in terms of what's difficult about making the database work well sometimes is clustering. What I see primarily in clustered systems is, from a support perspective, most of the issues that we see that are specific to clustering are about consistency and consistency repair. So there are two methods the database uses to manage consistency. So basically, a database receives data, it writes that data typically to two places based upon your replication factor, and then it's the database's responsibility, ideally, to make sure that those two different copies are eventually in sync with one another, right? And so that process is called eventual consistency. And it's eventual because we give ourselves sort of a grace period to make it happen, meaning that we can make that data available for reads, even if it's not fully replicated, which is typically the trade-off that most users in our space want. And so there are, right at the moment, two primary methods that we use to make data consistent if it can't be replicated immediately. The first is hinted handoff, and the second is entropy repair of compacted shards, or a feature that we've been working now on for about a year called anti-entropy, which turns out to be a relatively complex feature, but something that we've now are shipping and starting to use in production more and more. I have some thoughts on hinted handoff that I would like to share with you. Hinted handoff is basically sadness. So this is the first system I've worked on that has a hinted handoff system in it, and I'd have to say that I would never voluntarily build this model of consistency repair again. So how many people here are familiar with what hinted handoff is, just from a technical perspective? All right, so let me see if I can describe this quickly. Essentially, when you send a write to the database, if the database isn't able to fully replicate that write immediately, then it basically writes down the fact that it couldn't do that, and it basically journals the incoming write so that when the destination replica is available again to receive the replication, we can replay that journal, right, and we didn't just lose the point. So hinted handoff is basically just like a to-do list of points that need to be distributed in the cluster once the cluster can communicate with itself fully again. This actually sounds really nice, right? It sounds like, oh, I'm running like a 4 or 5 or 6 node cluster, and if one of my nodes is down and it needs to be receiving writes, I'll just remember that it didn't receive those writes, and I'll send them when the node is available. Sounds super simple. Turns out it's a horrible, horrible idea, in my opinion. So what are some of the problems with hinted handoff? The first problem with hinted handoff is the hinted handoff system is always the victim. Like, it has a real persecution complex. Anytime anything is going wrong in the database, the first thing that a user will typically see in a clustered environment is hinted handoff growing. Now, early on in the database, roughly maybe, well, about 2 years ago, the hinted handoff system was actually relatively immature, and it was super inefficient, and I think it left some battle scars on users that have been using the system for a long time. Most of those problems have been solved from an efficiency perspective. The replay of hinted handoff data is dramatically faster than it used to be. The persistence path is faster. The entire system is much more reliable. But it's still the thing that you see when the database is becoming inconsistent, or when there's a bad communication error, or data just can't be replicated, or the database is receiving more data that it can handle at any point in time. All of those conditions will cause hinted handoff journals to be built. So the first bad part of hinted handoff is it's actually a very noisy signal to our end users. Right? They just see hinted handoff growing, but it doesn't tell them really what's wrong. But it's often the first signal they see. Secondly, and I think more importantly than that bad signal, is hinted handoff really complicates load shedding. So a lot of people, I think a serious kind of complexity in running large-scale influx instances is that influx databases are relatively bad at load shedding, meaning that when the database is receiving more work than it can actually reasonably do in a period of time, either because a lot of telegraph agents have recently come online, or perhaps part of the cluster has failed and work has been consolidated to a subset of the nodes, the database doesn't have a way to kind of say, no mas, right? Please back off. It struggles with this. And if you've used the database in production, I'm sure you've seen cases where it becomes overloaded and falls into a bad cycle. One of the things that causes that bad cycle is hinted handoff. So once the database is in a degraded state, the surviving nodes now have more work to do. Right? This is the opposite of what you want. What you want is when the database is in a degraded state, you would like each remaining node to be able to do less work, or at least have some capacity to take work from the nodes that weren't present, right? So finding things that are less important and stop doing them for a little while. Hinted handoff is exactly the opposite. Now you actually have to write points to disk one more time. You increase I/O. You have to start replaying this data. It actually leads to a large amount of extra I/O when you're in a reduced functional state. Secondly, the hinted handoff queues really exacerbate a thundering herd problem. So when a node comes back online, or a cluster comes back online, in many cases, we'll have a large number of agents like Telegraph that have queued a fair amount of data that needs to be replayed to the database. Those agents are very resource constrained, right? They're small agents, often in small VMs, and so they'd like to be able to get rid of that data as fast as possible. And so when the database comes back online, they'll basically try to play that database back to the database at the maximum speed. At the same time, the database in many of these cases has its own journal of data, right? This hinted handoff points that weren't yet replayed, and it tries to inject those points into the incoming data stream as well, meaning that when you're trying to replay this hinted handoff data, you're often actually causing more work at a sensitive time of the system, right? When it's trying to reestablish itself and kind of become a consistent, stable cluster again. Again, that's an anti-pattern. That's not what you would like to do. Furthermore, in some cases, you can see patterns where Telegraph will write to the database will receive that write, journal it, understand that it can't be replicated, write it to hinted handoff, but the hinted handoff system will be backed off enough that Telegraph will hit a timeout and not realize that the database had persisted that data into a hinted handoff queue. And it's not always obvious to an agent or to a client when data's landed in hinted handoff. And that means that Telegraph will then retry that data. So now, in addition to having more data to do more work to do to catch up, you actually have work that's redundant in the system. Telegraph will be resending data to the database that is already journaled to hinted handoff. And again, this is another problem with the system, is that hinted handoff isn't really solving the problem, right? It hasn't clearly signaled to an end user that the data is safe and that it'll be replayed at some point in the future. Replaying data into the database actually causes other difficulties, because we have to dedupe it as we compact it. And so again, we've actually created more work for the system when it's in a reduced kind of computational state. The final problem with hinted handoff is that it's a relatively constrained resource. So journaling to the local, essentially ephemeral storage or SSD of a local node is a relatively constrained resource, and an end user can't count on that for any meaningful purpose. So people who really care about their data and really want to land it will often queue it in front of the database anyway. And in every possible way, those queues are a better implementation than hinted handoff. Right? They have their own resource pool. They can apply their own access control, right, based on business logic. They have a much longer persisted state that can be read multiple times. The data is available to a community of of programs and APIs, all of these cases, it's really much better than hinted handoff. So that's kind of my rant on hinted handoff and some of the complexities that are there. In terms of what we're doing to make hinted handoff better, essentially, we're going to be removing portions of it in our 2.0 architecture, right? We're moving to a system that's a little bit more of a shared nothing system, and certainly within our SaaS and kind of Kubernetes-based 2.0 implementations, we're introducing more functional queuing ahead of the database in place of hinted handoff at a storage node. A few things about kind of query, moving on from storage to some of the query patterns. You're all familiar with InfluxQL as a SQL-like language for querying the databases. I think the number one thing that I've learned about trying to scale users of a query system is that you should either implement SQL or you shouldn't. But implementing part of SQL or sort of a strange dialect of SQL has very little leverage. Most people don't know how to use it. It surprises them. The query language InfluxQL was built up over time as something that was meant to be super convenient to users, and it really certainly succeeds at that. It makes easy things really easy to do. But because there's not really any formal logic or formal algebra behind it, it's not a specified shared thing, there's only a single implementation of it, it actually makes it really hard to do hard things. Furthermore, it makes it really hard to know when an InfluxQL answer is correct. So if you're implementing a SQL system, there are a large number of SQL systems. Typically, people who implement an SQL processor will test their result versus the result of a third-party SQL system, and you can compare and you can at least decide which of you are right or wrong for a particular SQL answer. InfluxQL's proprietary nature and the fact that it doesn't have a formal logic behind it and it's not a particularly structured language means that it's incredibly difficult for us to guarantee that we don't regress or change InfluxQL behavior release to release. So in addition to load shedding, compaction, and hinted handoff, I think the other primary problem that I focus on a lot is improving the stability of a query answer, right? Not regressing query answers over time. So on this front, Flux is a very different experience. Flux is designed to be testable, it's designed to be composable, it's a much easier language to understand, it has a very formal specification behind it, and I hope someday to see multiple implementations of it so that we can actually compare one implementation to another and see that we're providing the same query results across both of them. Additionally, on the query side, and I think this is super important in the time series space, is it needs to be designed for contribution, meaning that I think Paul talked through this really well, but InfluxQL is actually one of the most commonly feature requested. I guess people file feature requests against the query language quite commonly, right, within our GitHub repository. But it's actually one of the most difficult parts of technologies for us to take contributions from. So it's really difficult for an end user to contribute to InfluxQL, in part because it's not well specified, in part because it's really a quite complex implementation, in part because it's difficult to test. All of these things are better, I think, in Flux, and that's very intentional, right? Certainly our intention to create a query language that can be openly contributed to. Finally, and I think this isn't surprising, but these query systems should all be designed to stream everything. Even if they're being primarily used in an ad hoc or kind of batch query mode, all of the resource modeling and all of the data transport should be designed to stream. And that's an implementation detail that certainly is being implemented with Flux from day one. So I've talked about a number of different aspects of the database that have been difficult for us to scale, or that I think you've seen as end users perhaps as common support causes. I like the system. I think it works really well, so please don't misread me as I talk about this. I just wanted to be really open about the things that we see as difficult. I wanted to be open about the things that I care about as an engineering manager in terms of making the database better, and I wanted to try to relate some of those problems that we see to the choices that we're making behind the scenes in order to make 2.0 a better and more scalable platform than InfluxDB already is. So the final part about this is thinking about how to be able to allow users in really large deployments to scale aspects of the database independently. And again, this is another kind of case where being good at shipping kind of the same functionality in different packages to different users becomes an important part of the company. So in many cases, if you've bundled everything into a single open source binary, you don't have a lot of scaling axes at your disposal, right? You basically have all of the functionality in a single place. But certainly in larger deployments, we would like to start being able to allow users to scale different parts of the database separately from one another. We have users that want to store a large amount of data but have relatively light query workloads. We have users more commonly that have really aggressive or bursty query workloads that would like to be able to scale query resources without needing to elastically expand an entire cluster. We have users that care a lot about data, that don't want data to be downsampled or lost in the case of a network disruption or a lack of availability of the database. They want to be able to queue those writes ahead of the database somewhere where they can be delivered at a later point in time. And we have a lot of users that want to be able to write like tasks or cron jobs or alerts or other relatively sophisticated kind of job-like activity against the database, and they'd like to be able to schedule those resources as well to run. And so as we go forward, we're thinking not only about how to make some of the internals of the database more scalable, some of the details like compaction and load shedding, but we're also thinking hard about how we can assemble a product that makes all of these kind of core components independently scalable while still presenting them behind a single unified API so that they look like a single product to the people who are using them. But they can be scaled by the operators running them in a more independent fashion. So that brings me to the end of my talk. I wanted to leave some time for questions. I hope this has been a little bit of a useful tour of the things that I think are a little bit problematic about InfluxDB 1.0, especially under a lot of load or in really difficult deployments. Certainly I'll be around today and I'll be around tomorrow if you'd like to talk about any experiences that you've had using the database or Capacitor or Flux or any of the other data management parts of our stack. I'd love to talk to you, and please find me. So any questions? No questions.
So you have these problems which you have faced, and I believe in the query space. What's your implementation for the Flux, and how you are solving your problems with Flux?
So if I understand the question, it's a little bit like, what are the problems with InfluxQL and how does Flux solve them? Okay, so what are the concrete parts of Flux that solve some of these problems? So, all right, so I think we can kind of boil the problems. I don't want to say this talk is super negative. I actually really love all these things, but I think we can boil down some of the challenges of InfluxQL into kind of three categories. So query correctness, the scalability of query planning, and query execution, right? And then the ability to actually manage large amounts of result set data, right? So it's sort of this kind of like streaming versus batch. And Flux really specifically approaches each of these things. So the InfluxQL planner essentially works by identifying, it parses the query and identifies all of the series that need to be read in order to compute the result of that query, and it creates basically a large list of those series in memory, which you can probably see a lot of memory utilization sometimes if you issue a query that has to talk to a large number of series. It then proceeds to kind of iterate across those series. It mostly groups all of the result set data in memory and writes it back. And Flux does really none of those things. So Flux has the ability, instead of pre-building a list of all of the series that need to be read, it can do that much more efficiently, and it kind of work over that list incrementally so that it doesn't need to allocate such a large amount of essentially plan data in order to run the query. So Flux has a much lower total memory utilization when running an equivalent query to InfluxQL when you need to touch a large number of series. So that's sort of the first thing that we've done. Secondly, Flux speaks to the storage tier through a set of defined streaming interfaces. So all of the data that Flux reads from the database is essentially read from a streaming implementation. So while the presentation to the end user at the moment for Flux is always that of an ad hoc query, under the covers it's really a stream processing engine, where it's streaming data out of the storage engine, pushing that data through a pipeline, and applying computation to it as it flows through that pipeline. There's actually a lot of sophisticated sort of like pipeline management stuff that's kind of in the internals of Flux that we haven't yet exposed to the rest of the world, but it has that concept in it. So for example, the storage iterators of the database all understand a concept of resource control and user. And so we can start to actually build multi-tenant resource fairness at the query kind of at the lowest level storage iterator basis, which is something that InfluxQL does not have. And then in terms of query correctness, I think I've talked about this a little bit, but Flux, the language, is eminently more testable than InfluxQL. It's also extensible. It's another key aspect. So I hope that answers a little bit of the question. Okay, excellent.
So, my question is, what are the main resource consumptions in InfluxDB? So, what drives the memory consumption and CPU? So, it's compaction process, ingest rate, and do you have some memory cache, and do you still have it when you support Flux?
Yeah, so the question is, what are the what are the key things that use the CPU, memory, and disk resources within the database, or what are the database processes that drive that resource consumption? And then there was a kind of a follow-on question about, is that still how does that relate to Flux?
So, you on picture had a memory cache.
Yes.
So, and this memory cache is for InfluxQL.
I understand what you're saying now. Okay, yes. So, so the things that primarily drive resource consumption in the database are the amount of cardinality of the system, right? So the database maintains a large index to make it efficient to find the series that you want to query. And so the larger the number of unique series that you have, the larger that index, and so the larger the footprint of that index becomes. And up to really, I think, like Influx 1.5 or 1.6, all of that indexing was in memory. Everything was shipped with an in-memory index. I think in 1.5, and then as a follow-on in 1.6, we started shipping TSI, which allows that index basically to be spilled to disk. The TSI index also has a large number of summary data structures in it to make it cheaper to compute things like meta queries, like show cardinality and show measurements and things like that. So, but still, cardinality definitely drives the one aspect of memory utilization. The other thing that really drives memory utilization can be queries that need to talk to a large number of series. So you can see a query spike memory utilization. And then I think primarily the thing that we see that mostly drives CPU utilization is compactions. You'll see compactions drive up CPU. Compaction is a very compute intensive process, and so you'll see that drive the CPU. And we'll talk about the memory cache separately. So, all right.
Thank you, Ryan. I really appreciate that. Before you go, I'm really sorry about your sadness.
I'm not sad, Mark.
But you said you were.
Well.
So if you were in marketing, we would think of hinted handoff is awesome, as opposed to sadness. So you might want to work on that, just to be a little more optimistic. So, but thanks a lot.